Check out this question, everyone. The question is a uniform cylinder bar AB, which is of mass m, is suspended using two identical springs. This is spring number one, and this is the spring number two, as shown in the figure. Now, what they are telling us is the spring two is cut. Okay, the spring two is cut, and we are supposed to find the acceleration of the center of the mass and the end A of the bar immediately after the spring 2 is cut. Okay. And what is the end A will be? End A is this end, which is where our other spring is connected. Okay. So do you want to try this thing, or I should solve it straight away? Do one thing, try it for a moment, then I will solve it. Okay. And as you can see, they have given us some direction for us to consider. No, they have told us to take the rightward to be plus x and the down vertically down to be our plus y. Okay, so you will have to give me answer in terms of this directions that is given to us. See, in order to figure out the acceleration of the center of the mass and even or basically the acceleration of this point A just after the spring 2 is cut, we'll have to find what kind of motion this rod will do. Obviously, it is going to do some sort of combined motion, no? And any combined motion of the rigid body can be understood by decomposing the motion that it will have, that is what it is going to do with respect to the center of the mass, which is pure rotational motion, and what will be the translational motion of the center of the mass, correct? But to get what is the acceleration of the center of the mass, or even the torque that I will have acting on this rod about the center of the mass, we'll have to know what are forces that will be acting on this rod just after the spring 2 is cut. So the forces that will be acting on this rod, one will be gravity, that is quite obvious. The other force will be the spring force. But basically, to find the spring force, what we'll be doing here is that the logic that we'll use here is just before cutting this spring and just after cutting this spring too, tell me, do you think there will be any appreciable change in the length of the spring one will happen? No, correct? Because it's not like the cutting of the spring is going to be an event which will be of some finite time duration. So what we can do just before the spring 2 is cut and just after the spring 2 is cut, the spring extension, whatever we'll have in the spring 1 will be same only, correct? So what we are going to do is we can find the tension, we can find the tension in the spring 1 or in each spring in the each spring just before the spring 2 is cut and when the rod was in equilibrium, no, when the rod was in equilibrium. The next concept that we have here in this question is when the spring 2 is cut, just tell me. So when the spring 2 is cut, the extension of the spring 1 cannot change immediately, no? The extension of the spring 2, spring 1 can't change immediately, correct? Or instantaneously also we can say. So basically what we are trying to tell here is that the tension in the spring 1 is same just before and just after cutting the spring 2, correct? And once we got what will be the tension in the spring 1 will have, that is the only force apart from gravity that will be acting on this rod, we'll be able to find what is the acceleration of the center of the mass will have and what is the alpha or the torque that we will have about the center of the mass. So once we know what the rod center of the mass is doing and what is the rod is doing about the center of the mass, we can calculate anything of for any point on this rigid rod, correct? So first we will draw the free body diagram for the case just before this spring, both of these two springs were cut. So suppose the tension whatever we'll have in both these two springs are going to be same by symmetry, we can say, just before cutting the spring 2. And this angle is 30 degrees theta and mg will be acting down. So what we'll have, we'll take components of these forces. So what we are going to have is t sine theta and t sine theta will be acting in upward direction. So 2t sine theta will be equal to mg, and sine theta is nothing but 30 degrees, so t will be equal to mg only, correct? This is suppose equation number 1. Then after cutting spring 2, after spring 2 is cut, so we will draw the free body diagram again. Now only forces that I have is this tension of the spring 1 and the gravity which is going to act. And what is the sign convention that the directions that they have told us to consider? This is going to be our plus x, this is going to be our plus y, and the one which is going to be perpendicular to the screen and going into the screen will be our plus z. And how I got that, that is going to be our plus z. So the direction of the direction of the plus z will be given by the cross product that I will have out of I cap and j cap, correct? So I cap cross j cap is going to point in this direction. So this will be the direction of our positive k cap. So which is going to be perpendicular to the plane and going into the plane of this board, correct? So next what we will do, we'll take components of this tension force. So one component I will have which will be t sine theta upward, another that I will have will be t cos theta along our plus x. So from this thing you will get the idea that our center of the mass is going to have one acceleration which is going to be along our plus x direction, which is suppose ACMX. Another that I will have will be in vertically downward direction, which is suppose ACMY. And it is the net external force in a direction which will decide what will be the acceleration of the center of the mass we'll have, correct? So this is what we are doing is for the translational motion of the center of the mass, no? For the translational motion or for the translation of center of the mass, correct? So what we'll get from here is net external force that I have acting along x will be equal to MACMX, correct? And the net external force that I have acting along y will be equal to MACMY. And what we have is only force that I have acting along x is t cos theta, which will be equal to MACMX. And the net force that I have acting in the vertically downward direction, you can find it is going to be mg minus t sine theta, which will be equal to MACMY. Correct? Okay. So copy this much. After copying, tell me, then I'll take a new page and there I will solve further. Acceleration that we had of the center of the mass by using this equation number, let it be, it is 2 and 3, correct? So what I will do, I will solve this. Next, what we will do is we'll figure out what is the angular acceleration that I will have about the center of the mass. That is nothing but we'll check out what is the torque I will have about center of the mass. So there's one more benefit we have on decomposing the motion of the rigid body, that is the translational motion of the center of the mass and pure rotation about the center of the mass. What is the benefit we have? Even if the center of the mass, suppose which is C here, if it is having acceleration, or if even if it is a frame which is a non-inertial frame, still will be able to write torque is equal to I alpha directly, because in case if you are writing down things from a non-inertial frame, you will have to consider the pseudo force. And where exactly will be applying the pseudo force? At the center of the mass only. So the torque of the pseudo force will become zero. So that is one of the benefit that we have on considering the torque about the center of the mass, correct? So the only torque that I will have acting about the center of the mass is the torque because of this force, which is t sine theta, correct? And the perpendicular distance or the lever arm that I have of the t sine theta, it is nothing but L by 2. So what we'll have is t sine theta into L by 2 is going to be equal to ICM into alpha. So from this thing, we can figure out what will be the value of the alpha we'll have. So now once we got the value of the alpha and even the value of the ACM, then to figure out the acceleration of the any point, what we will do, we'll consider decomposing the combined motion of this rigid body into pure rotation about the center of the mass and the translational motion of the center of the mass, correct? So we'll think as if one time we will consider just pure rotation if it is doing about the center of the mass with the alpha that we have calculated. So because of the pure rotation, what is the acceleration that we are going to get will be equal to L by 2 alpha, correct? Next, if I'll consider just a translational motion of the center of the mass, so here we have certain acceleration which we have got for the center of the mass. One is your ACM along x, another is your ACM along y, correct? And the sign convention that we have taken here is this is our plus x and this is downward is our plus y. So what we have is the acceleration of this point A because of the pure rotational motion about the center of the mass will be having minus of L by 2 alpha into j cap, correct? And because of the pure translational motion of the center of the mass, what will have? Tell me. The acceleration that I will have will be ACM x I cap plus ACM y j cap. And we'll take the vector sum of these two to figure out the net acceleration that point A will have. So the net acceleration of the point A from ground frame will be ACM x I cap plus ACM y minus of L by 2 alpha into j cap. So basically, only thing that you have to do now is to calculate the values of ACM x, y, and alpha and substitute in this final result to find the acceleration of the point A. And we can figure out whatever number 2 and 3 in this page. So we had t cos theta was equal to MACM along x, correct? And what was theta? It was nothing but root. It was nothing but 30 degrees. And the value of the t that we have from equation number 1 is mg. So we'll have mg into root 3 by 2 is going to be equal to MACM along x, correct? Will get cancelled. So we'll have ACM along x, which is going to be equal to root 3 by 2 g, correct? And next what we have mg minus t cos theta to be equal to MACM along y, and not cos theta, it was sin theta. And theta here is 30 degrees, so we'll, and t is equal to mg, so what we will get is mg by 2 is equal to MACMY, correct? Will get cancelled, ACM along y will be g by 2. And from this equation, we can figure out what alpha will have. So the moment of inertia of the rod about the center of the mass, how much it is? So this is our equation number 4. So we will simplify the equation number 4 by plugging the values that we have of ICM and all other things. So t sine theta is equal to, okay, well, let me write it down. T sine theta into L by 2 is equal to ICM into alpha. And it is t into 1 by 2. And basically t is mg. I will replace t with mg as well. So mg into 1 by 2 into L by 2 is equal to ml square by 12 into alpha, no? So here what we'll have is alpha will be equal to 3g by L. Check it out, correct? This is L, 3g by L, no? So now we can figure out whatever we'll have here. We are going to get root 3 by root 3g by 2 into I cap plus what we have ACMY, which is g by 2, and this will become 3g by 2 into j cap. So the acceleration of the point A will be equal to root 3 g by 2 I cap minus of how much it is? It is g j cap, no? And the acceleration of the center of the mass already we have calculated. It is root 3 by 2 g along positive x and g by 2 along our positive y. I hope everyone got this thing. So there's one more way to figure out the acceleration of this point P. What is that? And as you know, we can calculate the velocities that we had in the case of pure rotation using this vector result. For the tangential velocity, what was that? V was equal to omega cross r, correct? So as we know, the acceleration of any point in a rigid body with respect to the center of the mass will be pure rotational motion, correct? So the acceleration that I will have in the case of pure rotational motion when r is going to be constant will be equal to alpha cross r, correct? So the acceleration of point A with respect to the center of the mass is going to be the acceleration that I will have because of the pure rotation, which will be alpha cross r. And then further what we can do, acceleration of this point A with respect to the center of the mass, I can write as acceleration of point A, I will zoom it, it will be better. We'll write down acceleration of the point A minus the acceleration of the center of the mass from ground frame, which is going to be equal to alpha cross r. So the acceleration of the point A from ground frame will be acceleration of the center of the mass plus alpha cross r. And here we can calculate whatever alpha and r will have in the vector form. So as you can see, this alpha that we have here is in clockwise sense. So to figure out what direction of the alpha will have, we'll be applying right hand rule. Correct. And the way we have taken here the directions to be is this is our let me draw it. This is our plus x, this is our plus y, and this way into the plane of this board we have our plus z. And the way we are having alpha is in clockwise sense. So on applying right hand rule, so from right hand rule, what we have is alpha is going to be in clockwise, which is going to be in what direction? The direction will be plus k cap, no? So alpha we have calculated, and how much it is? It is 3g by L, no? So alpha is equal to 3g by L into k cap, no? And what is that position of that point A I have from the center of the mass? So location of A from the center of the mass. So where exactly it is, you can check out. So this is what we have is our point A, and this is what is our center of the mass is, no? So this way I have to go how much L by 2, which is our negative x. So it will be minus of L by 2 into I cap. So if you will plug the values of the alpha and r here, and if you will figure out the cross product, and after that if you will calculate the acceleration of the A, even though you will have to calculate what is the acceleration of the center of the mass we have from the ground frame that we know totally, correct? So using this thing also you will end up getting exact same answer, okay? So you can try checking out on your own this thing, okay? If you want, I will solve it from there, but nothing much to solve. You can verify that thing. I hope everyone got this two ways to figure out. This is quite simple, no? Just decompose the motion and check out what will have because of pure rotation and what will have because of pure translational motion of the center of the mass. Or other way around, you can do this vector thing, correct? As you know, the rotation of the motion of any point with respect to the center of the mass in a rigid body is going to be pure rotational motion. So this is the acceleration of the point A I will have because of the pure rotational motion with respect to the center of the mass frame. And once we know what center of mass is doing from the ground frame, we can calculate the acceleration of point A by doing this thing, correct? I hope everyone got this thing, and please verify whether you are getting the same exact result by this equation or not.